Hello everyone, this video is on section 11.5, the alternating series test. It's similar to the previous section in that it's kind of short, and I think it's more straightforward than the previous section, the comparison test. I think it's easier to apply. Okay, so let's dive right in. In 11.1, we got some practice writing these alternating sequences. So when we saw a sequence with this alternating positive negative sign, okay, we learned how to write those. And when we write them in this compact formula, we have this -1 to a power, where that power depends on n, right? And it doesn't, let's see, we have alternating sequences that start with a positive term and with a negative term, and we saw the difference on those. So if here I have my sequence starting with positive 1/2, maybe I would write it like this, with -1 to the power n-1, with my index starting at 1. And if my sequence started with a negative term, maybe I would write my sequence like this. Okay. And again, the key here is this power of -1. Okay. So just like we can have alternating sequences, we can have alternating series. So what does a series look like? That's when we're adding up these things with alternating signs, alternating between positive, negative. So maybe I have 1/2 minus 1/4 plus 1/8 minus 1/16, and so on. Well, I have this alternating sign on these terms, right? This is positive. Let's see, I have positive, negative, and so on. So again, I have this alternating structure. So my series I could write like this, okay? Where I'm adding up the numerical parts of these, follow this nice pattern. It's 1/2 to the n, right? But I'm adding, subtracting. So I can account for that with this alternating sign term here. Again, -1 to a power. And it works very similar to the sequences. Okay, I need to determine whether I'm starting on a positive number, a negative number, and adjust accordingly with this exponent here. And if you're ever in any doubt, once you've kind of written out a formula for this, you have your formula that you think is the formula for this. Check it. Plug in some n's to this and see what your first couple terms are. Okay. So really, these alternating series are easy to spot, right? If we see this alternating sign, if we see this alternating positive, negative signs, or addition, subtractions, we know that's going to be an alternating series. And if it's in this format, if we're given a series in this format, it's even easier, right? Because we just see this -1 to a power, okay? And that's going to be an alternating series. We might also see something more compact, like instead of having the -1 out here by itself, a series like this, we might have, or maybe we have this kind of series. Instead of seeing it in this kind of expanded form, we might just have something like this, right? These two series are the exact same. It's just this top, I've kind of split off that -1 by itself, right? So these are both alternating series, okay? And they behave the exact same. So we need to be able to recognize that this thing on the bottom is the same as the top, that it's an alternating series. So that's the one little caveat there. We need to be able to spot these alternating series. The good thing about alternating series is that they have really nice properties, and then testing it for convergence is fairly straightforward. Just like in the previous section, we're developing another tool to test for convergence or divergence of a series. Maybe we won't be able to figure out the sums of these series, but we can look at these alternating series and at least test them for whether they converge or diverge. Okay. So let's go ahead and look at the statement of the alternating series test. So let's let this sum from 1 to infinity, negative 1 to the power n, a sub n, be an alternating series with these properties. So it's got to be an alternating series, but it's also got to have these properties. All right. So this an, this part here, that's got to be numbers greater than or equal to 0. Okay. So that means this part, this an part, has to be my numerical part, but it has to be greater than 0, greater than or equal to 0. So for example, when I had the series negative 1 to the power n minus 1, 1 over 2 to the n, this 1 over 2 to the n, that would be my an, right? And I need to verify that this is greater than 0. Okay? If this part has, if this can be less than, if this is less than 0, that's going to screw up my alternating part, right? I only want my sign change to be coming from this negative 1 to the power n. Okay. So this an, this numerical part has to be strictly greater than 0. Okay. The second condition, I need that numerical part to be decreasing. Okay. It cannot be increasing. It has to be an plus 1 has to be less than or equal to an. So again, going back to this example we used a second ago, this 1 over 2 to the n, as n gets bigger, that term's going to get smaller and smaller and smaller, right? So I need that. And then lastly, I need that numerical part going to 0. So once again, returning to this example, 1 over 2 to the n, that numerical part, as n gets big, this numerical term goes to 0, right? Okay. So if I have all three of those conditions, then this alternating series is going to be convergent. And we would say it's convergent by alternating series test. Okay. And I'll go over the steps on how to use alternating series tests in practice in a few moments. But first, let's give a little argument about why this works. There's a proof in your textbook. You can check that out. But maybe looking at the proof, it wouldn't make, maybe it makes sense to you. If so, great, maybe not. So let's give a kind of intuitive idea of why this works. Okay. So let's consider our partial sums, right? Let's say I have a1 minus a2 plus a3 minus a4, okay, and so on. So let's say if I add up the first 4 terms, we'll call that S4. And if I add up the first 5 terms, that's S5 and so on. So let's look at these partial sums here. Okay. And in particular, let's start with S1. S1 would just be A1, right? Okay, and let's assume our first term is positive. Okay. So S1 would be here. Okay. Then what's S2? Well, S2 would be A1 minus A2. Okay. Right, so I'm subtracting a number away. So my term should, my second partial sum should be less than S1. But what do I know about A2? I know A2 is less than or equal to A1, right? Because that's my second condition. Okay. So I'm subtracting a number away, but I'm subtracting a smaller number here. So my S2 is not going to be all the way to 0, but it's going to be a smaller number, right? It's going to be like here. And then what would S3 be? S3 would be A1 minus A2 plus A3. So I'm adding that number A3 there. But so that should increase my number. but it's A3 is less than A2, so I'm not going to get all the way back up to S1, right? And then 4, S4, I would subtract away A4. But again, because these terms are decreasing, I'm not going to get all the way back to A2 either. So maybe you can see the pattern that these partial sums are going to kind of start ping-ponging back and forth, but their range is getting narrower and narrower and narrower. So I kind of don't have any choice but to converge to some value, right? You know, maybe I have this line here and my points are just going to keep ping-ponging back and forth around it. But eventually we're going to converge to whatever that value is. Okay, and that value might change depending on the series. But we can see that if our series has these 3 conditions, my series must converge. Okay. So a great example of this alternating series test and how powerful the alternating term is the alternating harmonic series. Okay, so remember our normal harmonic series, just 1 over n. We saw this for the first time in section 11.2 when we introduced series, and this is kind of the prototypical divergent series, right? This series diverges, and this is like the most famous divergent series. If you're going to learn one divergent series, you should know that this series diverges. This sum goes to infinity. But what if we add the alternating sign term here, this -1 to the power n? Okay. And it doesn't matter if our first term is positive, okay, or negative. Let's see, if I had n here, my first term would be negative. And if I had n-1, the first term would be positive. Okay, so that doesn't matter. They're both alternating series, right? So on the one hand, I have this thing is divergent, but let's check this one, okay? This looks like an alternating series. Let's make sure it matches my 3 conditions here, okay? Well, let's look at my numerical part, my an. Is that greater than or equal to 0? Well, 1 over n is always greater than or equal to 0, right? Check. Is an plus 1 less than or equal to an? Well, yeah, as n gets bigger, this term here is going to become a smaller and smaller fraction, right? And does the limit of an equal 0? Well, yeah, as n goes to infinity, this number is going to get closer and closer to 0. Boom. So all 3 conditions are checked. So by the alternating series test, this thing must converge. We don't know what it converges to, but it definitely converges. Now compare that to the this harmonics, the normal harmonic series. This thing was divergent. Okay, so we see that this alternating sign really makes a big difference in our series. Okay, and the application of the test is pretty simple, right? I use the test here. Okay, it was pretty straightforward. You know, I see an alternating sign, I check these 3 conditions, and I get my result. Okay. But let's be concrete about the exact steps we need to apply this alternating series test. Okay, so let's say I see an alternating series like this, and again, it doesn't matter if we start with -1 to the power n, or -1 to the power n plus 1, minus 1, whatever. Okay, as long as it's an alternating series, we use these exact same steps. Okay, first, we need to check our 3 conditions. We need to verify that this an part, this numerical part, is always greater than or equal to 0. Okay? So I need to be able to write it as like a -1 to a power, okay, power of n, n-1, n plus 1, and then all the rest needs to be a positive numerical part. So again, going back to that example, -1 to the power n, 1 over 2 to the n, I have my alternating sign part, this -1 to the power n, and then the rest, this 1/2 to the n, needs to be greater than or equal to 0. Okay? So that's my first condition. I verify that. Then I verify what my numerical terms are decreasing for all n. And then I need to find the limit of an. Okay? And then whether my series converges or diverges is really going to depend on what this limit is. So I find this limit. Okay? And then once I do these first 3 steps, I'm ready to make my conclusion. All right, let's talk about the easy one first. If the limit of these ANs is equal to 0, okay, then I have all 3 conditions of my alternating series test, and my series is going to be convergent, and I need to have a wrap-up sentence, just like with all my other tests. I need to say convergent by alternating series test. I've abbreviated alternating series test as AST here. On your own work, especially on tests, go ahead and write out alternating series tests, right? We're in this chapter where being wordy is a good thing, okay? If you're ever in doubt, write more. Okay. So again, if the limit of these ANs is equal to 0, our series is going to be convergent by alternating series tests. What if that limit is not equal to 0? What if it's equal to something else? Or what if the limit doesn't exist? Okay. If we have anything other than this, what is our conclusion? Well, as you might be able to guess, our series is going to be divergent, but we do not say divergent by alternating series test. We say divergent by divergence test. So go all the way back to section 11.2 again. Let's say I have a series Bn. Remember the divergence test. If the limit of Bn does not equal 0, our series is divergent by divergence test, right? That's exactly what's going on here. I have this series -1 to the n, a to the n, and this part's not going to 0, right? So this is stuff inside my series, call this stuff your Bn. Your limit of Bn is not going to 0. So our series is divergent by divergence test. Okay. So what I'm trying to hammer home here is when you see an alternating series, do your first 3 steps. Okay, verify your conditions 1 and 2, find your limit of the numerical part, and then based on this limit, we have 2 possibilities. If the limit is equal to 0, we're going to say convergent by alternating series test. If the limit does not equal 0, we're going to say divergent by divergence test. Okay, so very important point there. Now let's just see a couple examples real quick. So let's look at this one first. -1 to the power n plus 1, 1 over ln of n. Okay. Again, let's look at the positive version first. If I had 1 over ln of n, try comparison test on this real quick and see what you get. The short answer is, let's see, 1 over n, let's see. Let's compare 1 over ln of n to 1 over n. 1 over ln of n, and let's, just to be safe, let's start our series at 4. How about that? For n greater than or equal to 4, 1 over ln of n is going to be greater than or equal to 1 over n, right? Because what does n do? If I kind of graphed n, it would look like this, right? ln of n, on the other hand, looks like this. Okay, so 1 over n, let's see, I'm dividing by a larger number than over here, so this fraction is going to be bigger. So I expect to have this inequality. Okay, I know this series is divergent. So by comparison test, that series would be divergent. Okay, so that's going on when we just have the positive terms. But let's check the negative terms again. Let's check this alternating series. Okay, so now let's consider this alternating series. -1, what did we have? n+1. Let's check this thing. So what do I need to do? I need to do my 3 steps. Okay, this is my an, right? 1 over ln of n. Is an greater than or equal to 0? Well, let's see. For n greater than or equal to 4, ln of n is greater than or equal to 0. So 1 over ln of n is greater than or equal to 0. Okay, so that's good. Let's see. Is an plus 1 less than or equal to an? Well, ln of n plus 1 is greater than or equal to ln of n, right? So 1 over ln of n plus 1 is less than or equal to 1 over ln of n, which is what I want. Condition 3. All right, now I need to find the limit. What's the limit of that numerical part? Well, what's the limit of ln of n as n goes to infinity? Remember the graph. Okay, ln of n looks like this. It's increasing forever. It's increasing slowly, but it's increasing forever. It's going up to infinity. So the limit of 1 over ln of n, that is equal to 0, okay, which is the third point of my alternating series test. Okay, so I've checked all 3 conditions for alternating series test. So what's my conclusion? My series is convergent, all right? So I have my wrap-up sentence. I say it's convergent by alternating series test. Now, how can I show rigorously the second point that something is decreasing? Okay. I kind of gave a verbal argument here, but if we wanted to do it very rigorously, how would we do it? How can I show 1 over ln of n? How can I show that's decreasing, meaning an plus 1 is less than or equal to an? How you do that is turn this into a function of x. Okay? And I could rewrite this as ln of x to the power of -1, right? And then take its derivative. Let's say this is f prime is equal to what? -1 ln of x times 1 over x, right? Okay. So this is my derivative. So for x greater than or equal to 0, actually, let's see, our series is starting at 4. So for x greater than or equal to 4, this derivative is negative, right? And think about what a negative derivative means. That means our function's decreasing. F prime is negative for x greater than or equal to 4. So our series, our sequence is decreasing. For n greater than or equal to 4. So that's how we would show a sequence is decreasing. Last example, let's see this real quick. Let's consider this alternating series. I approach it, I see immediately it's an alternating series just by that alternating sign term. I check my 3 conditions. Is this positive or is this term positive? Yeah, that's always positive. Step 2, is this decreasing? Well, no, as n gets bigger and bigger, this I have a fraction greater than 1. So as I plug in a power greater than 1, it's not decreasing, right? And in fact, if I go a step further to step 3 and look at the limit, what's the limit of this thing? As n gets big, that is going to infinity. So my conclusion would be divergent by divergence test. Okay. So that's it. Section 11.5, as I said, kind of short, fairly straightforward. So good luck with that.